Should I start?
Sir, I think we can start in 3 to 4 minutes.
Okay, okay.
Uh, Hi, sir.
Yeah, hi.
I'll just first introduce you to the group. Hi, everyone. Good morning. Today we have amongst us uh, Professor Prasanna Ramamoorthy, and he joined IIT Delhi as an assistant professor in the Department of Management Studies 1.5 years back. That is in March 2019. And before that, so he did his BTech from Anna University in from 2004 to 2008, and then he worked in Mahindra for 4 years. But then I think then he went to do his PhD at IIM Ahmedabad. So there he spent nearly 6 years for his PhD till 2018, and he worked with Professor Sachin Jaiswal there on hub interdiction problems. So uh, uh, from there he has published in reputed journals like EJOR, European Journal of Operations Research, then also in Operations Research, then Computers and Operations Research, and after that, he went to Concordia University in Canada for his postdoc. So there, after a 1 year postdoc, he has come back to IIT Delhi. He has come back to India to join as an assistant professor at IIT Delhi. Professor Ramamoorthy, his interests basically lie in discrete optimization, large-scale optimization, and research interests are in hub interdiction problems and applications of large-scale optimization and discrete optimization. So I think this topic is a topic of large-scale optimization, as you must have decided, guess from the mail that you have got, also from the link. I think now I will pass it over to Aditya Hati to introduce the group to Professor Ramamoorthy.
Hi, sir. Good morning. A cordial welcome to you to our group. Yes, sir. SCML is a WhatsApp-based group created in 2019 by some of the like-minded people who have the tons of interest in the field of computing and machine learning. We are the people from various backgrounds, from academia to industries, like the developers, researchers from foreign universities, IITs, NITs, government and central government and private universities of India, PSUs, IT giants like Oracle, Goldman Sachs, HP Research, Eureka, etc. We are focused in the collaborative research and development of state-of-the-art technologies which can cater humanities at their level. That's all about us. Till now, we have arranged 5 webinars on the subcomputing and machine learning domain. We have a listen to grow mode. It is our pleasure to have you today with us. Sir, we are waiting for your interesting questions.
Okay. Can I start now?
Yes, sir.
Yeah. See, I thank SCML Group and the organizer Soham and Aditya for inviting me to give this talk. And I'm very happy that PhD students in our country, so they have started this group and they are organizing seminars, that too on a weekend. I like to see interested people doing this. Without doing much, I'll just say something about myself. So I work on this means optimization problems, but I work on integer programs mostly. I predominantly use exact methods, so I don't deal much with meta heuristics. Because I've never used it. Once in a while I use it, but it is not something which I do on regular basis. But exact methods, I have used most of them, so I try to go deeper into them. So without wasting much time, so I'll share the slide, so then I can start presenting. A window, your entire screen. Okay. So can you all see this slide? Guys, can you see that slide?
Yes, sir.
Yeah. So what I'm going to speak today is about large-scale optimization and a very specific technique known as Bender's decomposition. So large-scale optimization. So why this is necessary. So most of you would have studied optimization, and you know the difference between problem and problem instance, right? So problem is an optimization problem, and problem instance is a different data sets you are using to solve that optimization problem. So you would have noticed that the solvers like Cplex, Groby, any other solver, they solve this smaller problems very efficiently. But when it goes to this large problem sizes, so what happens is either the memory of the computer is out, which means you exceeded the memory of the computer, the RAM space of the computer, or you exceeded the time limit. So these are two issues which are regularly happens with solving large scale optimization problems. But as you know, with this big data and all this and all, so the data is becoming more and more larger. So we need efficient techniques to solve this large scale optimization problems. So that is the motivation of this talk. So now if I can solve 400 nodes hub location problems, then somebody would want to solve 500 node hub location problem, then 1000 node hub location problem. Or if I solve TSP with 1 million nodes, there is someone who wants to solve TSP with 10 million nodes. And these problems have relevant industrial applications. So from an industry perspective also, it is very important. It's not a very theoretical science to solve large scale optimization problems. Industry also wants people who can solve this efficiently. Also another thing is this problems when you are solving it, it should also give up the result very fast. Because these problems are decision problems, and decision is always accounted with cost. So if you are delaying in making a decision, the optimization problem is solving, but it takes 10 days to solve. So till then, you are waiting for the result of this optimization problem. So you're losing out a lot of revenue and other benefits you could have got if the problem would have solved faster. So this itself is a very active research area where how to solve this large scale optimization problems in a very, very efficient way. So this, I'll go to the next slide. So this is what I was speaking now. So so the research here happens in two ways. One is identifying good formulations itself. So that for a same problem you can have multiple formulations and find out which is the good formulation. So that is one type. Another is solution methodologies, how to efficiently solve a formulation. So in this talk we'll be predominantly talking only about the solution methodology. I'm not going to speak about dominating formulations. So now, so I am going to use a very specific problem of a mixed integer program, and I'm going to explain something known as Bender's decomposition. So this Bender's decomposition, so before that I'll describe these algorithms. This you would have known already. So one is approximate methods. So there are two categories. One is approximate methods. So the approximate methods has heuristics, which is very problem specific. Then there is meta heuristics, which can be applied to a wide variety of problems. This, as you know, there is no proof of optimality. The solution you are getting after some time, you are not sure whether it is the global optimum or the local optimum, right? So that is a drawback of meta heuristics. But an advantage can be in the absence of any good exact method, meta heuristic can be very, very useful. At least it can give a solution within 95% range, 97% range, etc. Right? So then there is the exact methods. Exact methods, there are several types. One is Lagrangian relaxation is there. Then column generation is there. Column generation is predominantly used for solving vehicle routing problems. Bender's decomposition is there. This is predominantly used for solving location problems, location routing problems, network design problems. Bender's decomposition is actually a superstar. You can use in a lot of cases. Cutting plane methods can be applied to a wide class of problems, but you need to identify good cuts. Then branching and enumeration methods. So this is branching and enumeration is methods like branch and bound, branch and cut, which you guys would have studied somewhere. In your optimization courses. So there are two types. So one is approximate methods and exact methods. So from a researcher's perspective, what is interesting is like if I have a problem instance, suppose I say like I have a problem instance of TSP, no, vehicle routing problem with 2000 nodes, right? If there is an exact method which can solve faster, the meta heuristics is of no use, right? So the exact method is solving faster than the meta heuristics. So the exact method is actually giving the optimal solution. Meta heuristic is going to give something which is approximate. So that this exact method dominates meta heuristics in this case. But meta heuristics can be used only when the exact method is not useful for solving that larger problem. So if 2000, if it is like 10,000 node vehicle routing problem, and if I cannot solve a column generation, then possibly I will use double search or anything. So you need to as young researchers, like when you are looking at an optimization problem, and you are looking at this the problem size, like the problem size you are going to solve. So like first try to solve by exact methods. Then like in case it is not working, then you go for meta heuristics. So why I'm saying this is, if you can solve by exact methods, it is the best thing that can happen to you, because you are getting the optimal solution. Whereas if you directly go for meta heuristics, which means you are getting like an approximate solution, then what is the use of an approximate solution when you can get the exact solution? So like for some problems, network design problems, hub location problem or facility location problem, Bender's decomposition can beat any meta heuristic. So it can solve like very large problems very efficiently, and that is why you see these papers are in very reputed journals like operations research, management science, etc. So that is why it is very essential to study exact methods. But unfortunately, a lot of people, they don't do exact methods. I think because it is theoretically, you need a very strong backing. Like you need to understand linear programming theory and like general mathematics itself, real analysis, everything. So yeah, so these methods are a bit mathematical. So, but if we invest time and do some sort of studying on it, it's a very efficient way, and it can do a lot of good to your life. So that is the summary of what I'm speaking. So yeah, this is how these algorithms are differentiated. So Bender's decomposition is like a particular algorithm which is used for solving MIP. But this Bender's decomposition itself is of several types. So there is classical Bender's decomposition. So this is the one which is used for solving MIP. Then there is something known as generalized Bender's decomposition. Then there is something known as logic-based Bender's decomposition, which can solve even IP, pure integer programs. So there are several varieties of Bender's decomposition, but I'm just going to speak about the classical Bender's. So this was developed by this guy, Jacques Benders. So this was his master's thesis. So he was, I think, he's a Dutch person. So this is his master's thesis. So what it does is it uses this divide and conquer technique. So what it does is like the MIP. So the MIP is a mixed integer problem. So it has both linear variables and integer variables, right? So it differentiates this linear and integer variable, and it solves one at a time. So it is very successful for solving problems that have large number of continuous variables and very few integer variables. So like location routing problems and all, if you see, so you are interested in locating like 10 facilities, but then the number of arcs connecting the customers to the facilities can be enormous, right? So in that kind of problems where the magnitude of number of integer variable to the number of continuous variable, if it is less, then you can use this Bender. Like it is like a straightforward approach, but you can use in other methods also, other way of optimization problems also, where you have like same number of integer variables, same number of continuous variables. So it works. It doesn't mean it doesn't work, but this kind of problems, it is a very good approach, definitely. So it will definitely work in these cases. Yeah. So okay, till now, do you guys have any doubt or anything? Can someone say?
No, sir, I think it's fine.
I have a question, sir.
Yeah, who is this?
This is Nitin from IIM Kashipur, sir.
Yeah.
Okay, so sir, as you said, we need to solve these MILP problem or large scale optimization problems ASAP. So I wanted to ask that in facility location case, the problems are generally strategic in nature. So okay. We are thinking of long term, let's say 5 years, 10 years down the line. So can't we even spend 5 or 10 days to solve it? Like what is the big issue? This could be a question.
Yeah. See, the thing is, this is a very specific case, but I will give you one example. So there is a optimization field which is coming known as online optimization. So in online optimization, what happens is, so this is used by companies like Uber and all. So at any instance, the decision maker, like the demand comes from throughout the city, and cars are also distributed throughout the city. So at any, like the demand is coming, the cars are also like they have to serve the demand. So at any instant you have to solve a vehicle routing problem. So if there are like I'm in Delhi, so in Delhi I have like suppose I say I have 2,000 Uber cars. At any particular instant there are like 200 demand which is coming, right? So the demand is say like the pickup point and the demand delivery point, right? So if you know vehicle routing, this is not a very easy problem, right?
Yes, yes.
So at any instance, I need to I need to allocate this demand properly so that my cost is minimum, right? So here I cannot wait for 5 days to solve the problem. So this decision has to be very instantaneous. So the optimization landscape itself is changing. So like previously, facility location, all yeah, it's strategic, but right now the kind of applications which are coming, they are all very very dynamic in nature, and you have to solve multiple optimization problems several times, right? So like I don't know like whether you have worked on vehicle routing, but you know how difficult the problem is. It's a very
Yes,
hard problem. And in a day, like suppose I am that Uber decision maker, so I am the decision maker in Uber. So if there is a request at 10, so if I'm taking every 2 minutes I'm seeing the request, so 10:15 there is a request, so there are like 200 requests, I need to allocate this cards to this request. Then 10:17 I have to again do this. So within 2 minutes I need to solve this problem. It's not it's so that is why this is very important. So most of the problems which we see is all like strategic in nature. So I understand what you're saying. So but even you look at this thing, this companies, this airline companies and all, so they have to make this crew scheduling, which is like which crew will go in which flight in the next 6 months, right? So the starting of the month they make this crew scheduling, but this problem is also a very difficult problem to solve. And if you know someone who is working in airlines, you can ask them. It takes like 6-7 days to solve the problem. They use column generation, but until unless they get it, they cannot do any planning.
Right.
But 6-7 days they are anyways losing out their time. So the once we are seeing as optimization, it is no longer there. So facility location, hub location, which is this kind of problems are not now required by the industry. So these problems are, what you're saying is right. It's strategic in nature. So you can spend 5 days if you want, like if you are actually solving that problem. But the real life examples, if you look at the industry, what is happening, so they don't have 5 days to solve this problem. So that is why it is very, very, very needed right now to use these methods. Okay.
Thank you, sir.
Okay, hope I have answered. So I will go to the. So
I have one it's Lakshay. I have one question. So is this Bender decomposition is only used for the linear programming, or is it used for the non-linear integer programming also?
Yeah, MIP means mixed integer program, no? So it is linear and integer.
Okay. Then. Thank you.
Yeah, so non-linear also you can use Benders, but that is generalized Benders. Pure integer programming you can use logic-based Benders.
Okay, thank you.
Okay. So you guys know what is mixed integer programming, no? Anyone has any doubts in that? Okay, I hope everyone knows. So I'm just going to give a brief intro of that algorithm. So what is happening? So this is the mixed integer program. So it is like it's a function of both y and x. So y is a binary variable and x is a continuous variable, right? So this particular this is a mixed integer program because it has both these variables. And what I'm going to do, so now what I'm explaining is like just how Bender's decomposition operates. Then I will come to the exact part of it, like how it is an exact algorithm. So how it really works. So the mechanism I will take an example and say, but I will just give some mathematical definitions now. So So this is a mixed integer program. So what happens in Bender's decomposition is, so you will partition it as a master's problem and subproblem, master problem and subproblem. So the subproblem will have only the continuous variables. So minimize C transpose X, dy plus bx is less than equal to d, right? So this dy, right? So this y is a solution of the master problem. The master problem gives solution of y. So y is fixed here, right? So the y is a integer variable which is fixed. So it is dy bar. So because it is fixed, it's a parameter now. So that's why I have represented by y bar plus bx is less than equal to d, or bx is less than equal to d minus dy, right? So this is a pure linear program because y is fixed, right? So then what I do, I take dual of this problem. So dual is like, if I take delta is the dual variable, so d delta, d minus dy bar delta is objective function is to maximize. Okay, so that is what is happening here. So this is my subproblem. So this is subproblem. Subproblem will give delta. Master problem will give y. Delta is a variable of the subproblem, which is the dual variable. Master problem will give a value of y. So what I will do, I will solve this master problem and subproblem continuously, and at each iteration the master problem is going to give the value of y, and with this y the subproblem is going to solve itself, and what it is going to do is it is going to pass a cut, which is known as the Bender's cut, right? So this is the master problem. So so this is how it operates. Like, you know, like each instance you get a y from the master problem and you pass it to the subproblem, you get the delta, then you pass a cut to the master problem. So this cut is this function, which is nothing but minimize delta. Delta is greater than equal to the objective function of the subproblem, but y is not fixed here, right? So this is Bender's cut. So now I'm very sure that you won't understand right now, but what happens is, it is like what you need to understand right now is, like, you solve master problem, you get y, then you pass it to subproblem, you solve it, then you will pass the value delta and create this cut. So each iteration you will solve, and the master problem is the original problem, right? The master problem is the original. This is the original problem, out of which I have relaxed this constraint, I have removed this constraint. So it is going to give a lower bound. The subproblem is a dual problem. So it is original problem is minimization, the new problem is dual, right? So it is going to give upper bound. So when the upper bound and lower bound converges, the algorithm stops. But I am very sure that you won't understand right now, but that's why I am going to explain it using an example, right? So this is the example. So here, so even if you don't understand whatever I thought before, now you will understand. So now my objective is to minimize this function 9a plus 10b plus 13c plus 4d subject to 4a plus 6b plus 3c plus d is less than equal to 12, a plus b plus 2c plus 2d is less than equal to 7, a, b, c are continuous variables, d is a positive integer less than equal to 8, right? So if I solve it in Excel, I am getting this answer. So a is 0, b is 1.5, c is 0, d is 3, right? So this is the solution of the problem. The optimal solution is 27. Now I am going to show how to solve this by Bender's decomposition. So first let me write like this. So let me write this function as v of d, this objective function as v of d. This v of d is nothing but, okay, it's not good. Yeah, so v of d, the original objective function was minimize v of d, na? So only this 9a plus 10b plus 13c is v of d. So the objective function becomes minimize v of d plus 4d. Sorry, 4d plus theta. Sorry, v of d is the whole objective. So 4d plus theta, where theta is the pure integer problem. Pure linear problem. Right? See here, d is fixed. So d is the solution which will come from here. Right? For any d, theta is the linear optimization problem. Right? So can you understand what I am saying here? So the whole problem is v of d. V of d is nothing but 4d plus this optimization problem. Right? Sometimes it works, sometimes it doesn't. It's fine what I'm saying here?
Yes, sir.
Okay. Right? So now what I'm going to do, yeah, so theta is this problem. Now what I need to do, so I have to, like, this is a minimization problem. This is a pure integer, pure linear program, because d is fixed. D is the only integer variable, so d is fixed now. So now this theta, because by strong duality, so this is a primal problem, then I am writing dual of this problem, right? By strong duality, the primal and the dual has the same objective. So theta can also be written like this. Theta is equal to maximize 12 minus d bar delta 1 plus 7 minus 2 d bar delta 2. 4 delta 1 plus delta 2 is less than equal to 9. 6 delta 1 plus delta 2 is less than equal to 10. 3 delta 1 plus 2 delta 2 is less than equal to 13. Delta 1 and delta 2 are the dual variables for these two equations, sorry, inequalities. So I have written the dual of this problem. By strong duality, they both have the same objective, so I can write like this. Theta is this. Now you can see here the feasible region. The feasible region is defined by these three half spaces or constraints. So it doesn't contain this d. So it is not dependent on d. In primal problem, it is dependent on d. Whereas in dual problem, it is not dependent on d. So what I can do is, now I can plot this feasible region. So the feasible region is this. So there are these three equations. I have this feasible region. So I have 4 corner points. Right? So for each of this corner point, I evaluate the objective, which is this 4d plus 12 minus d bar delta 1 plus 7 minus 2d bar delta 2. So for each of this corner point, I'm evaluating. So 4d, 2.34d plus 19.92d, 47 minus 7d for 15, 0.65 is 32.5 minus 90. So these are called as extreme rays. I will explain what is this. So delta is maximization problem. For any d, this delta value will be maximum of these linear functions, right? Because the optimal solution lies in the corner point, right?
Yes,
so
sir.
like,
Yeah, right.
just type in chat, like, you know, if you because I really don't know like how much you know linear programming, so that's why I wanted to ask every time. Yeah. So just like if you when I ask some question, if you say like you know this, just type in chat. Yeah. So yes, now I have this theta is the maximum of this 4 linear functions. So I'm plotting this linear functions. So first, this is the function 47 minus 7d. So for each value of d, I am plotting this. When d is equal to 0, it is 40. D is equal to 0, it is 47. Then it is going down. So similarly, this is the function 32.5 minus 9d. This is the function 4d. This is the function 2.34 plus 19.92d. So where will be the solution that for any y, for any d which is fixed, the solution lies in the maximum. So where is that line? Yeah. So it is right. So for any d, the dual problem, the maximum solution lie here, right? But the original problem is to minimize this maximum. So this is maximum, but this is to minimize this maximum. Minimize 4d plus theta, where theta is a maximization problem. The original problem is to minimize this maximum. So the minimum point is where? At d is equal to 3. This is the maximum line. And the minimum of this line occurs here when d is equal to 3. Right? Can you type yes in chat box? Yeah. Okay. So the minimum lies here, right? So also you can see this, and now I have shown before. The optimal solution is d is equal to 3 here, right? So the solution is also 27. So here also you'll find it is 27. Where it has gone? Yeah, it is 27. Okay. So now, but if I have to solve like this, what I have to do, I have to enumerate all the corner points. So here I have enumerated all the corner points. 4 corner points are here, right? So I have to enumerate all the corner points. But like if I have an equation, like if I am actually solving a hub location problem, facility location problem, if I have like 2,000 nodes, 20,000 nodes, I have like enormous number of corner points, right? So I don't have time to enumerate all these corner points. So like, you know, you understand what I'm saying. So like I don't have the time to enumerate all these corner points. So what I need to do, I need to like approximate this this maximization function. I want to approximate this maximization function. This is a piecewise linear line. So it is linear from here to here, linear from here to here. Because it is linear, it is also convex. Right? So I want to approximate it. So how I am going to approximate it? So that is what is going to happen now. So like I will add the support one at a time. So first I will add one support. So first I will add this line. Then I will add this line, right? So I'll add support one at a time. So this problem is what? The original problem is a minimization problem. So this 4 supports gives you this optimization problem. This solution, 27. But if I'm adding one at a time, so initially there were 4 constraints. Now I'm adding one constraint, then another constraint, then another constraint. So the objective is going to improve, the objective will be lesser than the original objective or more than the original objective. Can someone answer? See, I have a minimization problem. I have 4 constraints. Okay. Initially, I had 4 constraints, but what I'm doing, I've removed all 4 and I'm adding only 1, right? So it is going to be less than the original problem now because I removed 3 constraints, right? So it is going to give lower bound. So when I add this, sorry, not this one. When I add this one at a time, I'm going to get lower bound, but it will eventually come to the original. When I add all this 4, it is going to give me the solution, right? Yeah. So that is what is happening here. Yeah. So it is a lower bound to the original problem. So I call it theta bar D. The D is the solution at that particular iteration. So now I'm going to explain how this Bender's decomposition is working. So I will start at a value of D. So I don't know, I need to start somewhere. So I will put D is equal to 0. Okay. I will put D is equal to 0. Then what happens to this function? This dual problem. The dual problem is this, right? 12 minus D delta 1, 7 minus 2D delta 2. So if I substitute D is equal to 0, so I have this optimization. I have this optimization problem. So this optimization corner point is 1, 5, the objective 47, right? So now I need to add this support. Now theta I've got, I need to add this support to the original problem. So that I will get from the original theta, 4D plus 12 minus D delta 1 plus 7 minus 2D delta 2. So I substitute delta 1 is equal to 1, delta 2 is equal to 5. So I have the support theta 1D is equal to 47 minus 7D. So this is the first support I am adding. Okay. So this is the first support I am adding, 47 minus 7D. Now, my original problem is minimization, right? Minimum of the maximum of this, right? So the maximum occurs at 47 minus 70. Now I need to minimize this. So that is the master problem. I am saying subject to the constraint D is an integer and D is less than or equal to 8. So you find that the minimum happens at D is equal to 8, right? So the minimum is at D is equal to 8. Can someone type something? Yeah. So the minimum is at D is equal to 8. And at D is equal to 8, the solution is minus 9. The solution is minus 9 because you can substitute here 47 minus 7 into 8 minus 9, right? So this is a lower bound. This is a lower bound because I have added only one support. This can be optimal solution also, I don't know, because I am adding one at a time. But it is definitely a lower bound. Lower bound means it is equal to the optimal solution or less than the optimal solution. So it is the lower bound. So I need to evaluate the original objective for this D is equal to 8. So that I am doing here and I get upper bound. This is the original problem of the sub problem. So I'll substitute theta is equal D is equal to 8 here. So it is 32 plus 12 minus 8, 4 delta 1 plus minus 9 delta 2. So I'll substitute and I will get this problem. When I solve it, I get a corner point 1.66, 0. The optimal solution 38.64. So this is an upper bound. This is an upper bound because this is maximize 4y plus maximize 4 delta 1 minus delta 2. So actually it should be maximization should be here. So any feasible solution to the maximization problem will be an upper bound, right? So this is the total one is upper bound to the original problem, right? So because this is now what I have got, the upper bound is not equal to the lower bound because the upper bound is greater than the lower bound, which means I have not added enough support. So I will not terminate this algorithm. So I will do another iteration. So I will pass Now I'll pass this corner point and I'll add a support. So that support is here. So I'll substitute this. So I get now this is a now theta to d, which is the objective of the this problem. Master's problem is a maximization of two supports. So that first support is 47 minus 70. Now I have got another support. Now I added the second support. So this is a maximization of these two supports subject to this constraint. So this occurs at d is equal to 3 and the corresponding objective is 27. So as you can see this, so I've added enough supports. So I've got this minimum occurs at 27. Now I need to check whether this is optimal. So this is also a lower bound, but this lower bound is better than this lower bound. So this lower bound has improved. Initially it was minus 9. Now it has become 27. I need to check whether this lower bound is the solution. So I'll substitute d is equal to 3 in the original problem. So again it is 12 plus maximize 9 delta 1 minus delta 2. So here you get the optimal solution is 27, which means the upper bound is also 27. So I need not add any more supports. With two supports, I have been able to solve the problem. So this is how Bender's decomposition operates. So I think, yeah, so yes. Yeah, so do you guys have any doubts?
Sir, I have a doubt.
Yeah. Who is this?
This is Manish, sir.
Manish, yeah.
So, sir, when we are calculating the support, it depends upon the user choice of selecting the line equation, right?
No. So it defines the support. Now the solution defines the support. It is not like you choose which support to add.
So you're going from top to bottom. The equation which you got.
No, I am not deciding that. So I decided only at the starting solution and d is equal to 0. Okay, so I decided only that. So I could have chosen anything from 0 to 8. D is from 0 to 8. I could have chosen anything. I just started with 0. So you could have started with 1 also. It is not a problem. Okay. So, but the iteration generates the support. So the solution generates the support.
Hi, hello, sir. Can you please re-explain the second iteration?
So yeah. So I'll explain. So which one? This one?
The second iteration after this.
After this, no. Yeah. So I need to evaluate. So with delta 8, I have got a lower bound, which is minus 9, right? I need to see whether this lower bound is the solution to the problem, right? Which means the upper bound should also be minus 9, then it is the solution to the problem. The upper bound is coming from solving the sub problem. So I will evaluate this d is equal to 8 by substituting the sub problem objective function. So it is actually 4d plus maximization. Actually it's wrong because but it doesn't matter because anyways it's a constant. 32 is a constant. So this is the sub problem. By substituting theta is equal to, so d is equal to 8, I am getting this. So when I solve it, so the corner point is 1.66, 0 and the optimal solution is 38.64. Right? So the lower bound is minus 9, the upper bound is 38.64. So which means I have not added enough support. Right? So did you get what I'm saying here? Yeah. Yeah, so I have not added enough support. So I need to add one more support. So how will I generate that support? I will again substitute this 1.66, 0 in the original the support function. So now my optimization problem is minimize the maximum of these two support functions. 2.34d plus 19.92, 47 minus 70. So the minimum of these two functions happens where? Happens at d is equal to 3. Right? So at that time the solution is 27. Right? Now this is the new lower bound. My initial lower bound was minus 9. Now I got a new lower bound which is 27. So I need to check whether this lower bound is the solution to the problem. So how will I check? I will again check. I'll substitute in the sub problem. Sub problem also I get the same solution which is 27. So the lower bound is equal to the upper bound. So the algorithm terminates. So here I'm actually, this problem is actually minimize the maximum of these two functions, right? So you can also do like this. It's actually minimize theta theta is greater than equal to this function, theta is greater than equal to 47 minus 70. So that is the Bender's cut. So you can do like this. At first iteration, the Bender's cut is theta is greater than equal to 47 minus 70. The second iteration, it is theta is greater than equal to 47 minus 70. Theta is greater than equal to 2.34d plus 1992. So this cut is getting added. Like when the lower bound is equal to the upper bound, the algorithm stops. If it is not stopping, then this cut is getting added every time to the algorithm. Okay. So this is called as Bender's cuts. So further, what I'm going to do, I'm going to explain some improvements in Bender's decomposition. Just to if someone is interested and want to do further in this, so they can use these techniques also. So Bender's decomposition, see, right now Bender's decomposition, even it solves very large problems. Standalone Bender's decomposition does very well. Even now, you will find that it can solve very large problems very efficiently. Like meta-heuristics cannot compete with Bender's decomposition for some problems. Like this is from my own experience. I've seen Bender's decomposition is far efficient in solving a lot of problems. But there are a lot of enhancements you can do in this Bender's decomposition itself. So first is this Pareto optimal Bender's cuts. So what it does is, so this cut need not be an efficient cut. So so instead what they will do, they will solve one more subproblem and they will create a better cut than this cut. So after solving master problem, then subproblem, then another subproblem to get a better Pareto optimal Bender's cut. So what it will do, this problem it's solved in 2 iterations, right? So some problems might take 100 iterations to solve. So if you add a Pareto optimal Bender's cut, it can solve within 20 iterations, 30 iterations, something. It reduces the number of iterations, which is again reducing the time. Another thing is root node enhancement. Root node enhancement is you are first solving the master problem, right? So the master problem, at that time only, you can solve LP of the master problem using Bender's, LP of the master problem using Bender's, and add this Bender's cuts to the master problem, which means the root node is not without any constraint. So you have constraints by solving the LP of the master problem. So that is, this procedure was given by these 2 people, like Daniel and Devin. So this is also very efficient in some cases. This also works, like always it works. Another is branch and cut formulation of Bender's decomposition. So this is a very great improvement in Bender's decomposition. So what it did was, instead of solving a master problem every time, so the master problem is an IP, pure IP. The subproblem is a pure LP. So instead of solving this IP, the IP, how will you solve? You will solve by branch and cut. So you will branch and cut and you'll add and you'll find the solution, right? So instead what you do, so at every node of this original branch and bound tree only, you will solve a subproblem. So instead of solving multiple IP problems, there is only one IP problem, and it will add for every feasible solution to the IP, you solve a subproblem and you'll add a Bender's cut. So this one is very efficient. This can reduce even the normal Bender's decomposition time by 10 times, 15 times. So this is the, right now this is the vogue, everyone does this. So you cannot just do classical Bender's and escape now, you need to use this branch and cut formulation. So another thing is improving the starting solution. So here I started with d is equal to 0. So d is equal to 0 is I'm choosing randomly. So I could have chosen anything, right? But you choose what should be this d, right? By using some technique. So that is improving the starting solution. So this can also reduce the number of iterations, which in turn can reduce the number of the time taken to solve the problem. Another thing is variables pre-processing. So these 2 are there in this paper by Contreras. So in variables pre-processing, what they do, they fix these variables based on this reduced cost and shadow price at the IP level. So when you fix this integer variables, then it becomes constant, then the problem solves again very faster. So another is multi-cut Bender's. So multi-cut Bender's is useful in cases where the subproblem is very large. The subproblem, when the number of integer variables is very small compared to the subproblem size. So again, you cannot solve it by computer, but you can decompose the subproblem as small problems. In that case, you will add, instead of one Bender's cut, you will add multiple times this Bender's cut. So that is also an efficient way. So that was studied by these 2 people. So, but you can also refer this paper by this guy, Rahmaniani. So this paper, these are something which I have said, which I have used also. But this guy lists a lot of other enhancements of Bender's decomposition. So this is an interesting paper. If you want to study, you can read this one. So going further, like these are the papers itself. This is a paper with vendors. This is Contreras paper. This is the one that branch and cut vendors paper. This is multi-cut vendors. Then this is the one, the Pareto optimal vendors. This is again multi-cut. This is the root node enhancement, and this is the review paper. This is a review paper, and you can see that these are all published in very reputed journals in management science, operations research, etc. Yeah. So I am done with my talk. So if you guys have doubts, I'll be like to clear. Yeah. Anyone has any doubts?
Hi, sir. Good morning. Sir, is it
Yeah.
memory consumed
Abhaya.
the branch and cut? Yes, sir. Hi. The branch and cut you mentioned. So, is it like memory computation point of view how efficient?
Yeah, it is even efficient from memory point of view, because see, in vendors what you're doing, you are solving an IP, then a subproblem, then again an IP and a subproblem. No, so what is going to happen at this, when you solve this first IP only, you are actually branching, right? Cplex branches and it solves a IP, right? But instead, in branch and cut, what you will do, you will have only one IP. So the first IP only, the first IP has a lot of feasible solutions. So at each feasible solution, you will add a vendor's cut. So it is far efficient even memory wise. It will consider
we proceed like one by one step. So we need to carry the memory of like parents node, right? So is it?
so like what you're asking?
No. That's my memory point of view. Suppose we are like branching one node to other node. The way we proceed is the next step. So is it carrying the previous parent node memory also, right?
Yeah, it will have. But what I'm saying is there is only one branch and cut tree. So instead of having multiple branch and cut tree, depending upon the number of iterations, this has only one branch and cut tree. It will have. What you're saying is right.
Okay. Thank you.
Okay. So anyone else have any doubts?
Sir, this is Aditya.
Okay.
Sir, I have a doubt. That how do you solve for the problem of non-separable variables in optimization?
How do we solve the problem of
Non-separable problems for optimization, sir? Means the variables
non-separable means what?
Non-separables means the
Like
variables
they
are interacting with each other.
They are multiplied or something?
Just like that, suppose you have 10 variables, and within the 10 variables, 2 or 3 variables are interacting with each other. How do we solve these problems using?
No, then also you can decompose. See, I'll say you how to solve this as a facility location problem. So facility location problem has two types of variables. One is XIK, which is allocating a customer to a facility, and a facility location variable, which is YK, right? So this XIK is dependent on YK.
Yes.
Right, Aditya? Right?
Yeah.
So here also you can do this. YK is a binary variable. XIK you can make it as continuous and do Benders decomposition.
Okay.
Okay.
That depends upon the representation. Right?
Yeah. See, when you are represented as an optimization problem, and if it is a mixed integer program, directly start using Benders.
Okay, sir. Thank you.
Okay. So anyone has any doubts?
Furthermore, actually, I wanted to answer Aditya's question, because I have also read a bit on this separable and non-separable problems. And by the way, this is Nathan again. So Aditya, as far as I have studied, you need to check for the Hamiltonian function, and for the integer programming problems generally are the separable problems. So you can go by this, whatever sir has explained. That applies to like non-integer programming problems, but generally integer programming problems are separable.
Okay, sir.
Okay. I think no more doubts. I think.
Sir, one doubt, sir. So you had mentioned about earlier. You had mentioned about Bender's decomposition in nonlinear programs also.
Yeah.
Nonlinear integer programs. So
Yes.
among the advancements that you have mentioned later, so does any method cover the nonlinear variant of the integer program like MIP?
Yeah. Several of them can be applied actually. So there's variable fixing, pre-processing, Pareto optimals also works there. But you need to account for that nonlinearity. Like if it is actually interfering with this, what it is supposed to do, this particular enhancement you are using, then you need to correct it accordingly. But most of them, like you can directly apply. It is there. It is possible.
Okay, sir.
Okay.
So, uh, any more doubt, anyone? I think
Sir, one
there's no
question
doubt.
here.
Okay,
So
okay.
if you have two integer
Manish.
variables, yes, sir. So if
Yeah.
you have two integer variables in the decision, the minimizing problem, then the number of planes increases. It will be three-dimensional.
If you have three integer variables,
No, so I'm saying if you have two integer variables,
okay.
suppose you are solved here with one integer variable, right?
Right.
Yeah. So this is an example because just to teach, but but it works. Like you can have multiple integer variables, it still works.
That means that the line will be now the plane, right?
Yeah, it will be a plane. It will be a hyperplane.
Okay.
Yeah. Okay. So, anyways, see, what I want from you people is no, just now you have learned. You should actually go and code this. You should try to code this on your own and not try to see like whether we are getting into iterations or anything. Because unless you code, you will not actually you will not actually understand it very well. Another thing is once you code, then you can easily once you code a very small problem, then I think it will be very easy for you to code for very large problems, and I am very sure it will be very useful for you. So don't worry about that. Yes. So if you guys don't have anything more, so I leave.
Okay, sir. So Aditya, if you could just give the vote of thanks to sir.
Sir, this was a very wonderful experience for us. Your words are very wise and it will help us in our further PhD research. And I want to thank you on behalf of our group. I hope we will be keep in touch with you in future. Thanks you.
Thank you guys for listening. I'm happy that this kind of sessions are happening, and I'd like to sir, you guys you can use any method you want, but I need you to have your mind open and use exact methods also, because most of the papers which we see they come meta heuristics, but meta heuristics I think it is somewhat boring according to me. But it's up to you, like whether you find it boring or not. Yeah, but that much from my side. So thanks once again.
Thank you very much for your time, sir.
Thank you.
Thank you. Bye.
Thank you, sir.
Thank you.
Thank you, sir.